a hash. So you know that I used the letter H here to denote a hash function, and the question is, which hash should we be using? So on that, there's actually been a lot of progress in recent years, and so let me tell you a little bit about what's been done on choosing hashes for hashing passwords. Okay, so going back to the LinkedIn case, so LinkedIn, one of the crucial mistakes they made is that they actually used a very simple hash function. In particular, they used a hash function called SHA-1, which is a cryptographic hash function, and that's how they stored their passwords. Now, again, it turns out that if all you do is you use a simple cryptographic function like SHA-1, it's actually not that hard for an attacker to try lots and lots and lots of words. For example, the list of 360 million words that I mentioned before, just try those on the different passwords in your database, and in fact, within 6 days of the breach, about 90% of the passwords were recovered. Literally by just trying lots of words in the dictionaries and trying them very, very fast by exhaustive search, people were able to recover most of the passwords in the clear. In fact, by now there's dedicated hardware that will do this dictionary attack so fast that if your password is only even 8 characters, you can pretty much brute force the entire 8-character password space in just a few hours. Yeah, and as a result, any 8-character password that's stored hashed with SHA-1 on a database basically can be recovered in just a few hours. Yeah. So this is why you should never ever store passwords store a hash just using a simple hash function. And the problem is SHA-1 is too fast, right? An attacker who wants to try 1 billion passwords to see if one of those passwords is yours can just brute force through all the words in the dictionary, and SHA-1 is so fast that the attacker can run through those words very, very quickly. What we'd like to do is we'd like to make the attacker's job harder without slowing down the server too much. And so the way we want to store passwords now is as follows. Again, just to be clear, what we're worried about is the attacker breaks into the server and steals the password database. So what the attacker is able to get essentially is this list here of hashed passwords and salts. And as I showed you, this is happening over and over and over and over again on all the common popular websites and also on unpopular websites. So the attacker now has this list of hashed passwords, and his job is to recover the passwords in the clear so he can try to attack the user on different websites. This is basically what attackers try to do. So we want to make the attacker's job as hard as possible so that even if he has the password database, it's hard for him to recover the passwords in the clear. Okay, so the first idea is, well, suppose that the way we hash our passwords is actually not using a simple hash function like SHA-1, but instead we use a keyed hash function. So a hash function that to compute the hash function, you have to have a secret key. And an example hash function like this is something called HMAC, which again we discuss at length in the crypto class. So HMAC again is a function that takes as input the password, say, and the secret key, and computes a hash as the result. And this key, the secret key, is going to be stored in some hardware security module. So it's going to be stored in hardware somewhere, so that every time your server wants to test the password, what it will do is it will contact the hardware security module and say, hey, please encrypt, please hash this password for me using the secret key that's in your belly and tell me the result. Then the server compares that to the value stored in the database, in the password database, and if they match, they let the user in. Now, the point of storing the password in a hardware security module is that if an attacker, all they do is they steal the passwords, that's going to be of no value to them, because simply stealing the hashed passwords doesn't let them run through a dictionary and check if the hashed passwords correspond to words in the dictionary, because they don't know the secret key that's embedded in the hardware security module. Yeah? So stealing the hashed passwords is not going to do the attacker any good. Essentially, what the attacker is going to have to do is he's going to have to recover the password database, and then he has to interrogate the HSM online. He has to interrogate the HSM to see, one password at a time to see which password matches the hash password that the attacker recovered. Now, the HSM, of course, can implement rate limiting. Maybe it only responds to 1,000 requests a second, and then necessarily limits the rate at which the attacker can mount his attack. Okay, so this is all nice and good. So in fact, many popular web servers, in fact, use an HSM like I described here. But there are cases where you can't use an HSM. First of all, if what you're doing is hashing passwords on a phone, or hashing passwords on a laptop, or hashing passwords in an environment where you just don't have an HSM, then this is not really an option. The other issue is if the HSM for some reason is compromised and the attacker is able to extract the key from the HSM by whatever means, you would still like the password attack, the offline dictionary attack, to be difficult. And so the way we make it difficult for the attacker is we use what's called slow space hard functions. And so I want to describe a little bit what this means. And again, there's been a lot of progress in this area, so let me describe to you how this actually works. So the first set of slow hash functions that have been proposed and in fact used quite widely, one is called PBKDF2. This is password-based key derivation function, PBKDF2, and then bcrypt. These are slow hash functions where the slowness is actually controlled by a parameter. Okay, so the way you make the hash function slow is basically you take a cryptographic hash function like SHA-256 and then you iterate it many times, say 100,000 times. Yeah, so now for every application of the hash function, you have to run SHA-256 100,000 times. So if the poor attacker wants to evaluate like 360 million words in a dictionary, he basically has to run through the SHA-256 function 100,000 times for each one of the 360 million passwords. Okay, so that guarantees, that ensures that the password is actually slow and makes the attacker's exhaustive search much harder. Now, I should say, by the way, that we don't strictly iterate the hash function. That actually by itself is insecure. PBKDF2 and bcrypt do something more aggressive, which again we discussed in the crypto course. I don't want to discuss that here. But essentially, the fact that these hash functions are slow make it much harder for the attacker to try a large number of words and see which one matches the password. Now, interestingly, in fact, the number of iterations, so the slowness of the hash function, is controlled by a parameter that's given as input to the hash function. And so as CPUs get faster, as the hardware gets faster, in fact, you want to crank up the number of iterations so that the hash function still can only be done, for example, 1,000 times a second, despite the hardware getting faster. This is a very bizarre situation where actually you want things to run slowly. You don't want them to run fast. I don't know of many situations where, in fact, you want something to run slow, and if the hardware gets faster, you have to crank up your parameter to make sure that the hash function still stays slow. And the reason you want it to be slow is an attacker can't run through an entire dictionary and try one word after another. That's just going to take him too long. Okay, so that's one idea. But unfortunately, there's still a problem. And the problem is that an attacker is not going to run on the same hardware as your server, right? So your server is, or rather, your hash function is set up so that your server can do 1,000 evaluations a second, so your server can handle 1,000 logins a second. Yeah, that's kind of a reasonable number. Maybe you would have a few servers if you need to handle higher rates, but this is actually already a fairly high rate, sustaining, relatively decent-sized websites. And again, this is a parameter. I mean, if you need more, you can crank down the number of iterations and do 10,000 evaluations per second on a single machine. The problem is, on a regular server, you can only set the parameter so that you need to evaluate at a rate of 1,000 evaluations per second. The problem is the attacker is not going to run on an x86 machine like your server does. What the attacker is going to do, he's going to use dedicated hardware, for example, a GPU or maybe even an ASIC that can evaluate the hash function much faster than your server can on a commodity CPU. So the result is, because the attacker might be using custom hardware, the attacker can evaluate the hash function at a much higher rate than 1,000 evaluations per second. In particular, even though you set the parameter so that your server can do 1,000 evaluations a second, because of the custom hardware, the attacker might be able to do 1 million evaluations per second, and as a result, now he can still do the dictionary attack because of the increased speed. So I want to explain a little bit why is it that custom hardware is so much faster than a commodity CPU, and it's actually fairly easy to see. So here's a picture of what the Intel Skylake processor looks like. This is basically a 4-core machine. So this is 1 core, another core, another core, and another core. Yeah, so 4-core machine. And when your machine is essentially, when your processor is computing hashes of passwords, basically only a small part of the CPU is being used to compute the password. So you can see here, these are 4 cores, so these are the small parts of the CPU that are being used to actually compute the hash function. The rest of the CPU is being used for caching, for memory management, for various graphics operations, and so on and so forth. And so that really only a small part of the CPU is actually used for computation. Yeah, there's a lot of caching area that's being used on the chip. All that is irrelevant for computing a hash function, for doing a dictionary attack using a hash function. And in fact, when you look at the rates of custom hardware, the rates are phenomenally faster when you have a custom machine over an off-the-shelf CPU. So here, let me show you an example here. On an Intel Skylake x86, you can do about 93 million hashes a second. This thing only costs $1,700, so that this custom hardware is about 50,000 times faster than a commodity CPU. Yeah, and that's exactly why, and the reason is, again, these custom hashing rigs actually don't have cache management and all the other hardware that's used on an Intel CPU. Essentially, the entire processor is just full of these hashing engines, and that's why they can go so much faster. Okay, so because these custom hardware designs actually run so much faster, the fact that we use a function like PBKDF2 or bcrypt doesn't really prevent these custom devices from doing dictionary attacks. We have to do something different to make them, to slow them down.